So we're finishing up, actually we're going to start question 3, so undergrad researchers run amok. So this is getting to basically the second half of the exam, which is more the qualitative and the kind of physical understanding of 2 key properties, which is signal aliasing and spectral leakage. So let's read what the problem says. So as we always start off with, so undergrad researchers investigating rotational frequency of passive particles around a single active ferromagnetic particle embedded in a dense passive medium. Frequency, blah, 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 can you change? So we have 3 undergrad researchers. Let me get my pen. A, B, and C. Names removed to represent the innocent. Again, still hilarious, I am. So they've done DFT analysis, and here are the Fourier spectrums. So we're expecting, or we're trying to find frequencies, or we might expect to find frequencies at 2, 1.2, 3.6, and 4 hertz. Then we're given the Fourier analysis, or the frequency spectrums from our 3 researchers, and we're going to be asked to basically figure out what is Fs, N, and delta F for each of these researchers. So, and then we're going to kind of figure out, will we have signal aliasing or spectral leakage? So, if we're trying to measure these frequencies, to avoid signal aliasing, what is my rule? I need to make sure my Fs is greater than twice the largest frequency in the signal, so the Fs has to be greater than 8 hertz. For spectral leakage, I need to make sure that my delta F is going to hit each of these kind of values here. So one of the largest delta Fs you could have and still hit all those values is a value of 0.2 hertz. So let's see if any of these people did it correctly. So one thing you'll immediately notice, A and B are exactly the same. Again, there's a lot of times I'm writing this exam, I'm just kind of trying to keep you on your toes and make sure you're ready. But so A and B will have the exact same kind of values here. So we need to figure out, okay, what is our Fs, our delta F, and let's see what else the problem asks for, and N. So let's figure this out. So we know that delta F is equal to Fs over N. So we can kind of start to figure out what's kind of happening here. So let's look at A and B, for example. So one thing you'll notice, one really kind of difficult part of Fourier analysis is you're not sure, sometimes we always plot our Fourier analysis or our frequency spectrums from C of N from 0 to our Nyquist frequency, which is delta F times N over 2. So we shouldn't see any kind of mirror symmetry here to our Nyquist frequency. So this is that same value, N over 2. But you'll see here, both of these values, I'm going to use blue here, it's symmetric around the middle here. It's a mirror image of one another. So if you see mirror symmetry in a Fourier analysis, they plotted it basically not to delta F times N over 2, but to delta F times N. So we're not looking at N over 2 number of points, we're looking at the total number of points N. So if I want to find N, let me erase here now. So for A and B, it has mirror symmetry, so I know that I'm plotting to N number of points. So if I count my number of points here, ignoring the first 0 point, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. My N is equal to 40. So that, I'm going to erase that there. So my N equals 40 here. What is my delta F? That is another good question to kind of ask yourself here. So my delta F, I could see how many points do I get until the first kind of tick mark I can see is 2. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 points between 0 and 2. So my delta F, if they're both, we know that they're integer values, right? That they're equally, that they're going to be equally spaced between them. My delta F is just going to be that 2 hertz divided by 8. So what is that going to give me? So 2 divided by 8 is just going to be basically a fourth of a hertz. So that's my delta F. Now, if I have my delta F, so delta F is equal, we know, to 1/4. Now, my Fs is the last thing we're trying to figure out. What is my total number of points? N is 40. Switch that out. My Fs is equal to 10. 10 what? 10 hertz. That's it. We've got our answer, or at least one of our, or two of our answers actually, luckily for A and B, since this was repeated. So that's the analysis you go through. Now let's look at C. Is this mere symmetry? No. So we know that this is plotted to basically n over 2 number of points. So you could either set this, so we know that our Nyquist frequency is, so F Nyquist is going to be 5 hertz. You could also use this expression that Fs is equal to F Nyquist divided by 2, but we'll kind of skip that right later. So let's we know that this is going to be our Nyquist frequency. So we are plotting to n number of n divided by 2 points. So let's count our points again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 25 points here. So we know that that is plotted again to n over 2 number of points. So we are going to have, for C, our n is going to be equal to 50 for C. What is our delta F? Again, same procedure. So I have one value here. So 1, 2, 3, 4, 5. So I know that my delta F is just going to be 1 hertz divided by 5. So it's going to be 0.2 hertz for this one. And finally, if I want to figure out what is my Fs, I know that 0.2 hertz equals Fs divided by total number of points, n, 50. So what is my Fs? That is just going to be 50 times 0.2. You could do that. We don't necessarily need Mathematica, but it's always good to double check. Your Fs is going to be 10 hertz. So let's scroll back and answer kind of the second problem. So am I going to have, let's say for A and B, will I have signal aliasing? What is my sampling frequency for this value right here? 10 hertz, right? This sampling frequency for A and B is 10 hertz. So what about B and C, or excuse me, for C? It's also 10 hertz. So is that twice? Is our sampling frequency greater than twice our maximum frequency in this signal? So our maximum frequency is 4 hertz. We just kind of scrolled. We need to make sure our Fs is greater than 8 hertz. So we're fine for signal aliasing. We're good to go. But now the question is, our delta F, is it small enough to allow for, well, will it not give us spectral leakage? So what is our delta F for our first problem? Well, it's 1 over 4. So is this going to be an issue for us moving forward? Can we, or will we expect to see spectral leakage for A and B if our delta T, or if our delta F is 1 over 4? Yes, of course, because we're not going to hit 1.2, we're not going to hit 3.6. We need to make sure our delta F is at least 0.2 hertz. So that's not going to work. What about for here? For this problem, for C. Yeah, this one is sampled correctly. Our Fs is 10 hertz, so it's greater than twice our maximum frequency. 0.2 is going to allow us to hit all these frequencies we're trying to measure. That's it. C will work. We're good to go there. So yeah, so let's see what else this problem is asking us. So it says a new theoretical, so we've answered A and we've answered B appropriately here. So what about C? A new theoretical paper has come out and finds a very low rotational frequency of 0.01 hertz and a higher frequency of 10 hertz. The DAC I'm using can sample at 10 kilohertz and can collect a total of 100 points. Also, the sampling frequency must be an integer. Can my undergrads correctly sample this signal? Why or why not in terms of spectral leakage again? So there's a new frequency, or a new theoretical paper comes out. So we are now measuring, we have to hit basically this 0.01 hertz. Actually, I'm going to switch out to my red. So new frequency, 0.01 hertz. Maximum frequency now is 10 hertz. So this is those are F max, maximum frequency in our signal. So our DAC can sample at 10,000 hertz. And we could collect a total, so our N max would be 1,000 points. Also, our sampling frequency must be an integer value. So can my undergrads correctly sample this signal? Why or why not in terms of spectral leakage? So if we're trying to figure out, we're trying to measure these two frequencies here. So my delta F needs to be at least, so delta F has to equal 0.01 hertz. And so because we want to hit this signal and we want to hit this signal here, our F max. Additionally, we need to choose a sampling frequency, Fs, such that we are at least greater than 20 hertz, twice our F max. So let's say I sample at, we need our delta F to be 0. We know that delta F is equal to Fs divided by N. So if I want to make sure this is 0.01 hertz, and then if let's say I sample at 30 divided by N. So let's see if we can do this. I'm going to go back to Mathematica. I'm going to and actually I'm going to pull it to the side here. Let's see this side by side. Solve this function. You guys can do this, but I like to always double check my math, and I just like to code in Mathematica. It's always fun and relaxing, so I'll never get my math wrong. Begin. 3,000. So at 30 hertz, I'm going to able to measure my, I will not have signal aliasing because I'm greater than twice 20 hertz. My DAC can only get me a data points of 1,000 though. So am I going to be able to sample the signal correctly? No. Let's say I even pushed it to the limit. Let's say I just did 20, which again would give me signal aliasing. I can't, my DAC is not going to allow me to give me enough number of points. So I cannot correctly, I can avoid signal aliasing, but I will get spectral leakage in this problem. So my undergrads, I kind of set them up for failure at this point. So that one is on me. So even if they try to do the correct analysis, or actually they should come back to me and say buy another DAC, but again, that's another answer or another discussion for another day. But yeah, that's it. So problem 3 is done. Now on to the last one, and then you're done. So on to the next video. I'll see you there. Thanks. Have a good one. Bye.